Welcome back to the workshop. It looks like there is one more example for us to take a look at for differentiation. One of the things that's a little bit interesting from Calc 1 is implicit differentiation. Related rates is frequently a topic considered using implicit differentiation. So, which is typically not students' most fond area. Anyway, so I want to take a look at one more example just to help you guys out, make sure we know what's going on there, because I wouldn't be surprised if we see some implicit differentiation this semester. So let's take a look at that example as well. So here is our relation, right? This is not actually a function, I don't believe. I would have to double check on that, but what we can do is we can find dy dx, and it may depend on y as well, which is perfectly fine. So when it comes to taking the derivative of x cubed, that's not a problem, right? We did that before and we found that to be 3x squared. But what's interesting next is the y cubed. So why is that interesting? Wouldn't it just be 3y squared? No, because the variable here, right? We're saying that x is the independent variable and y is the function. So we're taking the derivative with respect to x. We're not taking the derivative with respect to y. So y is some function, right? Y of x is equal to something. I don't know what it is, but y is a function of x. So what we actually have here is we have a function being raised to the third power, which means we have a composition. So we do have 3y squared because we have something being cubed. So the cube is the outer function in our composition, but then we have to multiply by the derivative of what's inside. And then the function on the inside here is y. What's the derivative of y? Well, it's y prime, or simply dy dx. Maybe not simply, but whatever version you want to use should be fine. So composition says that we have to take the derivative of the outside function, multiply by the derivative of the inside function. Now, in our implicit differentiation here, we take the derivative of left, and it's equal to the derivative on the right. So we have, of course, the -1 is going to go away because the derivative of a constant is 0. But here we have a product. So the 6 can carry along as just a constant multiple. So we can call it 6 times the derivative of x times y. So the derivative of x times y requires the product rule because we have x times some other function y. And the derivative of x is 1, so 1 times y, plus the derivative of y is dy dx, so plus x times dy dx. At this point, we can begin to simplify things a little bit. So let's call this 3x squared plus 3y squared dy dx, not really anything to do there, is equal to 6y plus 6x dy dx. How exactly you simplify things is up to you. That's absolutely fine. But if I want to solve for, right, find dy dx. If I want to find dy dx, I've got to get dy dx on one side and everything else on the other. So I'm going to go ahead and subtract 3x squared from both sides and subtract 6x dy dx from both sides. So that's going to give me 3y squared dy dx minus 6x dy dx is equal to 6y minus 3x squared. Subtracted this from both sides, subtracted that from both sides. I'm left with this common factor of dy dx on the left, which is good because I want to solve for that. And after I pull that off, I have 3y squared minus 6x. And this is equal to 6y minus 3x squared. Of course, divide by the coefficient, something times this. This is the coefficient on dy dx. So dy dx is equal to 6y minus 3x squared divided by, right, divide both sides by this, 3y squared minus 6x. Of course, there's a common factor of 2 in the common factor of 3 in the numerator and denominator here. So you might want to continue simplifying that to observe that this should be 2y minus x squared divided by y squared minus 2x. Let's see here. I don't think you can factor those. No, because that would have to be a difference of squares, and those aren't squares. So that's it. All right, so my apologies that there was one more example on differentiation. The rest is practice for you guys to take a look at, and I would encourage you to do so. Lots of space for this last problem. All right, thank you for your time. I'll see you guys back in the workshop in a little bit for anti-differentiation.